So, hi guys, welcome to High Entropy, and this is another series, or you can say, I just thought the way I'm learning DSA won't help me uh, showing up every day, but you are just trying to solve one or two problems. Sometimes you are unable to solve a single problem, and that is not a grinding. So, why don't I start? Like, I'm staying up uh, till morning sometimes, so it's better if I learn. Otherwise, I will end up with 1 year or 2 year. Even after that, I will won't feel confidence in DSA. So right now, I'm just lying on my bed, sitting on my bed, not lying, and it's just comfort. Like I'm sitting comfortably on bed instead of sitting on chair. I decided like I will stream like this. This is a just comfortable stream. I just kept my iPad on my lap and laptop on bed. Sometime I'll keep it on lap, laptop in lap, on lap, not in lap. By the way, so I'm not sure if you can see my screen because I'm just planning. Like I miss if some, I know sometimes some people message rarely, but still I should respond to them. So I'm not sure how to just connected my account here, but still I feel like it's not working. Let's see if it will work. Just let me see. Hey guys, why it's not working, bro? Open a stream. I don't know. I just searched it on. I don't know, man. What's wrong with it? I don't see any chat or something. Maybe I need to check. Hmm. I have to explore it. Let's see. Stream via Shardy. What is a Shardy? Chats. Hello. Hell. Bro, what the fucking is it? It's not working? No, I don't want this. What's the meaning of it if it's. My camera not working or what? Oh, there is latency. Sorry. Stream not started. My camera not working or what? Oh, there is latency. Sorry. Open stream. Bro, I'm opening a stream. Stream not started. My camera not working or what? Oh, there is I think I should stop it instead of that. I'll let me open stream. It's not helping me. Bro, I'm opening his screen. I will fix it later. So now it's let's jump. Let me close it. I think I should stop it instead of that. I'll take you forward. So I'm just solving the graph problem. I will continue with that. Depth first search, based breadth first search, cycle detection in directed graph. So I already tried it in the last stream, and I was not able to solve it. I was getting idea, but not sure how to preserve the. Suppose I will show you what I was thinking. I will tell you like my thought process about it. So quick time player. I think it's not ready. Hmm. What's wrong with it? Where is my solve it on paper 3? So what I was thinking, 0, you are going, oh it's very awkward to sit here, 0, then 1, then 2, and so it's directed graph. This is first directed graph. Before it I just solved undirected one, but that is not the problem. Adjacency list will be same here. Instead of like A to B, B to A, there will be only an A's between in one direction only, you can say. So for example, what I was thinking, like I will pick any node, like these are the nodes 0, 1, 2, 3, 4, 5. Sorry, I'm not sharing my screen or what. So these are the nodes, correct? So you can say I will make a visited array. This is my thought process, but seems like will stuck somewhere. So there will be like these are the nodes that you will maintain whether it's visited. So 0, 1, 2, 3, and 4, and 5. So for example, you will start with any node. Let's say you will start from 0 to 5, and if any node is not visited, then what you will do, simply you will start you will apply DFS, depth first search. For example, you are starting from 0, let's say, so you will go to 1, you will go to 2, you will go to 3, you will go to 4, and every time what you will do, just imagine it is a recursion. So first you pushed 0, then 0 will call 1, then it will call 2, it will call 3, it will call 4, and then after 4, what you will say? You will see 1 again. So you will just look into it, like whether you already visited it. So right now we don't have any. I don't know if how to approach or look back from here. For example, you are at 3, then you will say, "Am I visited 2?" You can definitely you can make visited array. Like for example, you can mark 0 visited, 1 visited, 2 visited, 3 visited, 4 visited, 5, and so on. So 0, 1, 2, 3, 4 will be visited. Hmm. Okay, so that you can mark. But the problem here is, imagine you started from some another node and you are visiting it for the second time, but it is not the basically it's not the source, or it is not a part of cycle. Then there will be issue. So that's why I need some sort of approach where I can say, okay, this is one thing, for sure it will be cycle. So you just need to look back if the node is visited and it is still part of the cycle, or it's part of DFS that you are traversing right now. For example, this is now the stack that you created from 0 to 0, 1, 2, 3, 4, 4, and after that you are again trying to access 1. So you'll say, okay, wait, 1 is already visited, and also it is part of stack right now. I'm just trying to create an example where It is visited but not a part of, you can say, cycle. I will just create one example because I have one doubt, buddy. So this is one example where you can say, okay, you can simply generalize that, okay, you are visiting one, then why don't you, mark everything visited, zero visited, one visited, and if something that is already been visited and you are trying to visit it again, then you can say it's a, basically it's a cycle. But that is not the case. Based on visited or non, I was thinking in the same way, but somehow when I thought about the corner case, it will fail. Let's say zero, then one, then we have two, okay, then we have, let's say, three, correct, and let's say we have four. I'm just thinking, let's mark like this, correct. Now I think this will be work. Okay, so suppose now you, what you will do, you will say, okay, zero visited, one visited, you will mark, two visited. Suppose you are starting from here, so you will mark this one visited, 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 and after that you will start for three. So you will say, oh bro, three. You will try to reach to two. So you will say, okay, two is already been visited. So why do, so there is a cycle, but it's not. There isn't any cycle. To be honest, this is a new graph that is trying to visit the same node. So that's why you need to start from here. Okay, you are going to three, and you will say, okay, I posted the three. Now I will try to visit two, and two is not a part of it, so it cannot be. So it's not. It's new, basically new graph, a new component of graph, or you can say new edge from which you are starting. So how to look back into the stack? This is my question right now. Look back into what you have visited. Oh, so one thought that is coming into my mind, why don't I create, like every time when you are calling a DFS, for example, right now we are calling DFS. So it could be like here you are calling, basically you, what you will do, here you will say, okay, I'm starting from zero. So this is one node from which you are starting. So this will be source, and from here you are going to traverse in this direction, and this will be one of the component of graph, you can say, though it's connected, but this is one of the, you can say, branch. When you are starting from here, you can go till here, and for this node you have to really start visiting from here. So what you will do, you will mark everything like what is visited, not visited. So zero, visited, one visited, two visited, sorry, it will be something like, this will be now global one, what you, whatever the, nodes that you will be, you have visited, zero, one, two, three. Okay, let's say, let's take example, so suppose you did this. Oh, if it is the case or condition, then it will be covered by anything. This one, it will be part of it, right? It will be starting from here to here. Hmm. Global visited. I will make a global visited array, and what it will do. So I don't know what, if I'm audible or not. Okay, it's okay. Let me see if anyone is pinged, because last time, can't I drop chat box here, talk chat? I have to log in, bro. Oh, wonderful. I don't know how to log in. Perfect. Oh, leave it. So 0, 1, 2, 2, 4, 3. So I need to do something else. First is global, where I'll keep everything. Then what if I'm calling DFS, and let's say from 0. So you will call DFS 0 visited. Visited, and another one stack or something, and then you will call DFS 1 visited, and you will put the last value into stack. And every time you will say, whenever you are getting a node and it is visited, then you will check whether it is part of it or not. Current stack. Is it worthy to do it in this such a way? Let's do, bro. This is the one option that is coming into my mind. So right now, I will solve it using this approach. We have adjacency in the form of what the heck? Represents using adjacency 1. Okay, 0 is connected to 1. I mean, they created 0, 1, and second 1 is connected to 2 and 5. 1 is connected to 2 and 5. Okay, adjacency we have already given. So let's build a DFS. First I will create DFS function, DFS depth first search. Here I will call self. Self basically referencing the object itself, basically the first parameter. Like when you are calling, suppose, okay, leave it, bro. You already know if you don't know basic Python. So okay, another thing, node. We need node from which you are going to adjacency is readed for sure. Okay, any other thing? Yeah. Hmm. So other thing will be visited, and stack. I will call it stack. Let's see how it goes. So now what you will do? So every time whenever you are going to, so you have to check neighbors. So this node will be already marked visited. Now from this node, you are going to explore all the nodes. Depth first search you will do, and to perform depth first search, what exactly we are going to do? Basically, we are going to explore all the neighbors. So node, we know node. So for NBRS, neighbor in ADJ of node. So for this node, what are the neighbors? If not visited, what? So we'll say, okay, if node is not, if neighbor is not visited, then but bro, how many stacks will be there? Lot of stacks will be there. For example, from each node, a lot of things. This will be horrible. I mean, every node, at each node you will create a stack. For example, from this node you can, uh, hmm, maybe you are starting from 0. Let me think more, bro, about it. Okay, let me think clearly. So if I will, like, let's say you are starting from, let's say there isn't any point from here. So what you'll do, you will start from, you will call DFS of 0, and from 0 you will call DFS of 1, and it will call DFS of 2, DFS of 4. Logically what should be, when you are calling DFS stack, so at starting here you have 0 only, it should be something like 0. Now you have 1 as well, then you will be having 4 as well, no, 2, then 4. So these are the nodes. Now suppose you are at 4 and somewhere you got, let's say this is also node, so now you got calling 4 to 3, and DFS of 3 will try to call DFS of 2, but you will say okay, 2 is already visited. So now you will check, let me see, if 2 is part of this continuous stack, so you will say okay, so you won't call 2 because it's visited. So but 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 you will check whether this node is already in this stack. But at each node you have to decide. For example, at DFS of 3, so you are at DFS of 3, and might be you have 2 3 branches from here. Let's say DFS of, you are trying to call 1, DFS of uh, 0, DFS of something else, and some of them are visited. So non-visited, then you will call another branch. Yeah, you will call another branch, and if it is DFS of 1, then you will just check and whether it is matching with anyone. If it is, then you will mark. So it's already stacked. So why do we need to create a stack? 0 1 2 4. So first you have 0, then 1, then 2, then 4. Okay, what I think, why don't we collect all the visited node in the graph? For example, it could be like DFS of 2 is already visited, so just will return 2 from this, and so you will return true. Now you will check whether 2 is matching with this or 2 is in this result. If it is, then you will return true, and if you are getting true from anything, then you can return. So in this way I can basically, every time when I'm returning something, you will check and you will return two things: true and visited value, visited access. And whenever you are trying to access a node that is already being visited, that has already been visited. Is it efficient? I don't. I'm clueless, bro. Okay, but I will solve it using this approach. After that, I will check the tutorial. Phew. Wow. So first neighbor adjacent. Oh, sorry. What I'll do? First, I will call. I don't need to stack now. I will just do one thing. If neighbor in adjacency node. Oh, okay, okay, okay. Let's do one thing. So node been already visited. Now you are from. Okay, for neighbor in adjacency node, if not visited of what neighbor, then what you'll do, result is basically self dfs neighbor adjacency visited, and here you will mark visited of neighbor equals to 1. Okay. huh. Result, what you are expecting in the result will be, there will be uh, true or false, and an array containing the nodes that are visited, and you try to access them. Okay. Stack, I will say. Else, if not visited. For each neighbor you are calling. DFS, right? If not, that means it's already visited. So if the node is visited, then okay, let's do one thing. So here we'll call global stack for this branch. Else global stack dot append. uh, so this neighbor is visited, and you are trying to add it. Okay, so this is one good thing. And if status equals to true, I don't need even to maintain status. If a status, simply return true. Else we need to check. Else what needs to be done? Global stack dot extend. Oh god, I'm not sure if stack will global stack dot extend globe stack. So all the nodes you are adding into it. And now you will check. So if node in global stack, then simply you will return true, and you don't need to return anything, just return true. Else return uh, false and global stack. Is it worth it solution? I don't think so. This is one thing. Now for each node you are going to do this operation. You will call node, you will check if anyone is trying to access it. At each level you are going to check if anyone is trying to access it, and if not, so visited is equals to 0 for underscore in range, basically n. So you got visited array, and now for uh, v node in range n, if not visited node, then what you'll do, simply you will say okay, you'll call self dfs, and here we will call result self.dfs, and here you will pass node. You will mark, don't forget to mark visited of node equals to 1, and node you are marking visited, then adjacency you are passing, then visited you are passing. I feel it's a very lengthy, it's not a efficient approach. I don't know why it is running into my mind. So, but let's first try to solve it. So, okay, if not visited node, visited one, you are marking this. If result and stack we don't need to, so I will keep like this here, because you are starting for the different graph component. If result, then simply return true, and at the end don't forget, if you haven't got somewhere, return false. Jai Mata Di. I will do this here. If you are returning somewhere true, return this, return false global stack. Woohoo! Solved it, bro. Wonderful. Happy hooray. Huh. Let's take a moment and happy, 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 happy. This is Bakwas. Guys, anyone watching? I don't know. Nitros, क्या की बातें? In the night. Cloud Code builds ugly website until you do this. I think I should focus on AI. More important. Someone is watching. Are you following me? I mean, following in the sense like whatever solution I'm writing. You can text me if you need. I'm just watching my own stream, bro. Sorry. It's like someone is watching. By the way, I need to put. Are you following me? I mean, Validating says like whatever solution is going. Sorry. You can text me. I'm just watching my own screen. Okay. Sorry. I will mute it. Mute हो जा. So let's do one thing. Let's jump to another problem, and what I'll do, because I'm able to solve it using this approach, but if you have any doubt I can explain it. Simply what I'm doing at each step, just I'm storing whatever the visited node I'm trying to visit again, and then I'm looking back to them uh, from a node where I call DFS, and checking if I have tried to visit this node anywhere. That means in this path, in this DFS, basically traversal, what you did, simply you tried to access the node that has been already accessed. So yeah, that's what sort of approach. And here I'm simply blindly, if you got anywhere true, you don't need to worry about the stack and all. You can keep it empty. But not sure if it is efficient approach. So I don't want to watch tutorial right now because I will be confused with the two approaches. It's better if I'll stick to one, whatever is coming into my mind, because at the end, uh, basically you have to solve the problem. So if you are remember, definitely I will watch the tutorial to get better approach if needed. But I will keep one note here: must watch the tutorial. uh, I think they should do one thing. One thing I observed here that can be better. For example, whenever you are solving and you are submitting the solution, I don't know where is the feedback option. I wanted to give one feedback. It's not a feedback, but it's a recommendation, or you can say a feature suggestion. One thing, I'll tell you what exactly I wanted to suggest them. it will be it would be great for the revision purpose. Suppose right now I just submitted one solution, and you might submit multiple solution for a problem on different maybe month and all. So why don't they keep one option here to tag the solution, so that you can keep it like a revision 1, revision 2, somewhere like here, maybe one more uh, tab or column should be here. So I was looking for feedback option or something, but let's leave it right now. Let's focus on problem solving. Oh, it's new, completely new. I never heard topo sort. What exact? I think it's topo sort means topological sort. Then I heard the name. What is topo sort? Oh, in graph. Oh, it's topological sort, but I just heard the name. I never maybe gone through the algorithm, and if I have gone through the algorithm maybe during my college time, then I'm not sure. Maybe just for marks, I learned it hardly that time. By the way, let's first go through it. Then I will watch tutorial definitely to get better. But first I will try. I just wanted to try out like if based on the text only I can get it or not. Topological sort is a linear. Okay, let me do one thing. I will keep it aside, and I will keep it like this. It's more comfortable. So topological sort is linear ordering of vertices in a directed acyclic graph. Sort is a linear ordering of vertices, linear ordering of vertices in a directed acyclic. There won't be any cycle. It is very uh, famous, especially in data engineering and other activities, like you have to build a tag. There won't be any cycle, but it will be like from going from one direction to some, like A to B, B to C, C to D, D to E, something like that. And Okay, a topological sort is a linear ordering of vertices in a directed acyclic graph, such that for every directed edge from vertex u to vertex v, such that for every directed edge from u to v to vertex v, u comes before v. U comes before v. Okay, I think. Okay, let's. Whatever they are telling, I think picture can describe it better than this. That's why visual representation gives us more information, or it's easy to understand. Human can easily understand from visual diagrams. So let's see. Can I expand it somewhere? Oh, bro. I just want to set. Just want to see the image, bro. Open image in new tab. Okay. So we have given unsorted graph 0 1. Oh, one thing, let's do it 0 to 1. Why don't I copy it on copy image, and let's do it here. Paste. Ah, oh, got it. So better I will draw something. Let's do it. Where are you, bro? Oh, you are here. So we have a graph 0 to 1 and 1 to 5, 1 to 2, 1 to 0, 0, then oh, based on diagram, what I see from a node, all the nodes, basically uh, all the edges from, like, let's say u to v, there is a edge, and u to uh, p is a there is, u to q is there is. So what will happen? You will come first, then you have to decide pq. Let's imagine this as a box, pq and v. So always you will be before it, and now you have to, in the same way, you have to basically think about pq and v. So for example, here we have 0 to 1, 0 to 2, 0 to 1, 0 to 2, okay, 1 2, and 1 to 5, 1 to 2, 1 to 5, 5, 1 to 2. No, no, no. 0 to 1, 1 to 0 to 2. So these are after 0, 1 and 2. So is it algorithm? Like how to sort it? Yeah. And then for 6, 6 is coming after it, because you will see 6 to 1. That means 6 should be before 1 and should be before 5. So 1 and 5 should come after 6. That's why you will see 1 and 5. And 1 to 5, 1 and 5, 1 2 goes 2 and 1 2 goes 5. So 1 2 goes 5, 1 2 goes 2. Okay. So I got it. Better. I mean, if I have to read the article, definitely I get confused quickly. But here it's better better. Let me. I will just once read whether I'm understanding or not. Key rule and concept. Directed a cyclic graph. The graph must have one way, edges, and no loops or cycle. Okay, that is the meaning of DSA. Dependency order. If task A must happen, if task A must happen before task B, okay, that means A to B. Then A appears first in the sorted list. Okay, multiple valid orders. Oh, okay. This is the new property. So for a graph, there could be more than one topological ordering, topological sorting. Can we build? Can we draw for this one? 0, 1, 2, and 1 to 5, and 1 to definitely this is okay. Tasks, common uses, task scheduling, figuring out which job to first when project depends on either steps. Oh, hmm. Course prerequisite. Yeah, this one is the important one because in data engineering, most of the times what we do, you can take any example. You are scheduling basically whatever the, for example, you are building a ETL pipeline or you are building any orchestration work. Now even in you can say in generative AI and all, there also we are just creating graphs, maybe lang graph or something in the chain lang chain. We are using different approach, but wonderful. Yeah, this is one of the important things to be honest. When you are deciding, okay, this one will run after this one will run because there are so many dependencies. Oh, it's interesting. How to solve it? Main algorithm depth first search and how to say it? Cons. It won't be cons, right? It will be cons. Ah, let's now. Now. I will watch tutorial. First thing I will stop it. Okay, let's do one thing. Hello, bro. Sorry, just close this. Now I will do one thing. I will go to weekend. No. This is not one. I will close it and I will close not this one, but striver. See, detect cycle in detect directed graph. This is done, and lot of unnecessary tab I have created. What? In a directed graph. When I solved it, I think this one and this one are linked, interlinked. That's why it is showing. But let's do one thing. Topo sort, not on YouTube. I will watch here only. Solve. Let's focus on it. Oh, what happened to voice?
Find it, I can say it only exists on that which is directed acyclic graph. It means any directed graph which does not have a cycle. Why? I will tell you that. So basically, the definition states any linear ordering of vertices, means these nodes, any of the linear ordering, such that if there is an edge between U and V, so that there is an edge between U and V, U always appears.
Sorry. From starting.
In this video, we are going to learn about topological sorting, and we're going to solve this using the DSA algorithm, which is the depth first search. Now, what is topological sorting? In order to define it, I can say it only exists on DAC, which is directed acyclic graph. It means any directed graph which does not have a cycle. Why? I will tell you that. So basically, the definition states any linear ordering of vertices, means these nodes, any of the linear ordering, such that if there is an edge between U and V, so that there is an edge between U and V, U always appears V in that ordering. U always appears before V in that ordering. So this is the particular tag. So let me write down the edges that we have. I think we have an edge from 5 to 0. We have an edge from 4 to 0. We have an edge from 5 to 2. We have an edge from 2 to 3. We have an edge from 3 to 1. And we have an edge from 4 to 1. So 1, 2, 3, 4, 5, 6. We have all the 6 edges. So this can be a possible linear ordering. Why? Let me tell you that. 5 to 0. 5 appears before 0. 4 to 0. 4 appears before 0. 5 to 2. 5 appears before 2. 2 to 3. 2 appears before 3. 3 to 1. 3 appears before 1. 4 to 1. 4 appears before 1. So thereby, this is a valid linear ordering. Similarly, this can also be a valid linear ordering. So if you see 5 appears before 0, 5 appears before 0, 4 appears before 0, yes, 5 appears before 2, yes, 2 appears before 3, yes, 3 appears before 1, yes, 4 appears before 1, yes. So this is also a valid ordering. There can be multiple valid orderings, but we just need to figure out one of the topological sortings, and that should be good enough. Now coming across, we will understand how to find it, but why only in directed acyclic graph? Why? So first let's understand why in directed graph. So what does the definition state? If there's an edge between U and V, U appears before V. So if you take undirected graph and you see that there is an edge between 1 to 2, it actually means there is an edge between 1 to 2 and there's an edge between 2 to 1. So how can you write the ordering such that 1 is before 2 and 2 is also before 1? And it's not practically possible. Thereby the directed graphs are only possible. Now why acyclic means no cycle, means no cycle? Why is that?
I know. So let me tell you.
1
So
to 2,
because
3 to 2.
Because suppose so here you won't be able to decide like one should come before 3 or after 3. There is a dependency, so it's like starvation. 1 depends on 3, 3 depends on 1. Okay, so 1 according to 1, if you are taking 1 as a source, then 2 and 3 should be after it. But if you are taking 3 as a source, then it should be like 1 and 2 should be after 3. And similarly, if you are taking 2 as a source, then you will say 3 should be after it. Also, 1 should be after it. So you won't be able to decide.
1. Okay. So what I'm stating is 1 is having edge to 2, which means 1 should be before 2 in that ordering. 2 to 3 is an edge, which means 2 should be before 3 in that ordering. 3 to 1 has an edge, which means 3 should be before 1 in that ordering. That is not possible. Why? Because there is a cyclic dependency happening. Thereby, if there is a cycle, you cannot have an ordering such that everyone follows that. So thereby, acyclic and graph is. So I hope you got the reason why is topological sorting valid, or why can we just write a linear ordering for a directed acyclic graph, which is nothing but a DAC. Okay, so the reason is clear. Now let's quickly jump up to the algorithm. So we have this particular tag and we have the corresponding adjacency list for this particular tag. So what is this particular topological sort algorithm in DFS states? Now what we will always do is, you know that, right? We always have this particular stuff for components, and that is the same thing we will be following over here as well. So over here, how many nodes do we have? We have 5 nodes till 1 till 5, and we will say if not visited, yes, very important, if not visited of I, then we will call the DFS for I. Yes, that is how we will do it, and I'll explain you slowly. So this is what we will take, and we will always declare a visited array. So let's quickly declare the visited array squarely. We can do that over here. So we have declared the visited array, and make sure everything is marked as 0 initially. Marked as 0 initially, and let's quickly start. What is the value of I? The value of I is 0 initially. Is that visited? No. So what you do is, you start the DFS call from 0. Remember this. You start the DFS call from 0. At the same time, just declare a stack. Yes, declare a stack. And what is a stack? It is a last in first out operation data structure. Last in first out operation data structure. If you don't know, please you know about stack. So DFS of 0 is there. So what you do is, you say, okay, this guy is visited. Does 0 have any adjacent nodes? No. So the DFS will not call any for the DFS, and it will go back. But remember, before going back, take the 0 and put it into the stack. Before going back, take the 0 and put it into the stack. Done. So the DFS for 0 is completed. And
Wait.
going back, not call any for the DFS, and it will go back. But remember, before going back, take the 0 and put it into the stack. Before going back, take the 0 and put it into the stack. Done. So the DFS for 0 is completed. Next, I'll do the execution going forward, don't worry. Next is 1. So again, you write the same thing, DFS of 1. The first thing you do is you mark it as visited. Does 1 have any adjacent nodes? No. So there will be no further DFS calls. No further DFS calls. So before going back, put this into the stack. Then you put this into the stack, and now you will go back. So the DFS is completed. Next, it comes for 2. So what happened? Any adjacent nodes? No. So there will be no further DFS calls. No further DFS calls.
Oh, for
So before
0
going back,
there isn't any edge. All are incoming edges, not any outgoing edge. So in degree, our degree is 0. So that's why you kept simply whenever you are going from a node, you are adding it into the stack.
Put this into the stack. Then you put this into the stack, and now you'll go back. So the DFS is completed. Next, it comes for 2. So what happens is, you call the DFS for 2, you mark it as visited. Now 2 has an adjacent node, so you go and call it for 3. Now what you do is, you mark for 3 as visited as well. Now does 3 have an adjacent node? It checks that 3 has an adjacent node 1, but if we carefully see, we cannot call for DFS of 1. Why? Because it is already visited. Yes, because it is already visited. So thereby, what we will do is, we will be like, okay, it is already visited, so let's quickly just not call any further DFS calls and go back. But if we're going back, take that 3 and put it in. Now we go over here, no further DFS calls, go back. Before going back, put that into the stack. So we have put that into the stack and we're not done. Right? Now, the value will be 3. 3 is already visited. Next value will be 4, and that is not visited. So what we will do is, we will go and check out for 4. Now for 4, we will mark it as visited, and we will check if there are adjacent nodes. 0 is visited, 1 is visited. So both of the adjacent nodes are visited, so there will be no further DFS calls. So you go back. Now what you do is, you take this 4 and you put it into the stack. Take this 4 and you put it into the stack. Right? So next, it will be 5. And now next the DFS call will be happening for 5. So you mark it as visited. Does 5 have any adjacent nodes? Yes. 0 already visited. 2 already visited. So thereby, go for the DFS calls of 5 and you put 5 into the stack. Done. Now I can say that the DFS call is over. Once the DFS call is over, whatever you stored in the stack, take it one by one. The first thing that you take out is 5. Next thing you take out is 4. Next thing 2. Next thing 3. Next thing 1. Next thing 0. This is one of the linear orderings. Yes. This is one of the linear orderings that you can get. Very, very important. This is one of the linear orderings that you can get, and this is what is known as topological sort of this particular graph. I hope that does make sense. Now you must be thinking about, hey, Shrek, but what is the intuition behind this algorithm? The algorithm looks very simple, but what is the intuition? What is the intuition?
No.
Let's first write the code, absorb the logic, and then I'll tell you the intuition. The intuition is very small. Don't worry about that. So as usual, I'll write the C++ code on the right and define the Java code on the left. Given the V and the adjacent matrix, we will be declaring the visited type. Let's quickly declare the visited and declare. Then we call it, and we need to just do, keep on doing it.
Fuck. What is the intuition? I think maybe I'll solve a couple of problems, then it will be easy. So what exactly steps are there? Simply,
The stack is not empty. So
let's grind it. I will take the same graph that he used, so it will be easy for me to follow. Where is your graph, bro?
this is one of the linear orderings. Yes, this is one of the linear orderings that you can get very, very not visited of I. Then we will call the DFS for I. Yes, that is how we will do it. I'll explain it possible. Now why?
Yeah, let's take example. And let me draw first. Let me note down the example. So 5, you are going to use 0, and then from 4 you are going to 1, and from 3 you are going to 1, from 2 you are going to 3, and you are going to 2. So this is our graph. Where is our graph? Oh yeah, it's a. So first thing, what exactly we are doing? Topological sort. And so steps. Step 1, create a visited array, and from stack we are not popping out anything, so you can take any list and you can post the item, and from the end you can start, like for example if you got something and top to bottom, like you just need to traverse, you are not every time like adding or inserting, so you can start like traversing. For example, if you got something like at first you added 0, then you added 1, then you added 2, then at the end you want to traverse, so you can either you can start or you can reverse it, one option, or you can just do traversing from last to first in this way. So we'll use, and even you can use stack, but in Python I never used stack. I think it will be in the library, but I can use dictionary. No, sorry, I can use list here, append, and at the end what. So why, if there is data structure already available built in, not inbuilt, so So step 1, create a visited array and mark everything uh, non-visited. Mark everything 0, means unvisited, non-visited, whatever you say. And now what I'll do, you will start uh, picking a node from, let's say, 0 to n minus 1. These are node. For each node, if not visited, step 2, iterate 0 to n. If not visited, just what you'll do. First thing, call DFS. Okay, and on DFS call, what you will do, simply whenever you do DFS call, you know what you do. Okay, mark it visited and call DFS. Okay, and at the end, whenever you are getting out of DFS, for example, you call something like DFS there, let's say here it is 1 and here it is DFS 2, and whenever you are coming out of this, for example, you got the result for this when you recursively call, then just add it into stack, push it into stack. Yeah, push pop, push and pop, last in first out. Popping we are not doing anywhere, just pushing. We will do pop at the end. So DFS of 2, and after that you will pop. And for this one, definitely you need to add at the end. Add at the end. Okay, so this is one option, and you will do the same operation for all, and we can get it. It's straightforward. But I'm curious to know another one, cons, how to pronounce it. Cons algorithm. Let's see. Is it cadence? No, cadence is for array or something, I remember. It's pretty famous algorithm. Okay, let me keep it aside for a moment, and then I will just start writing code for 334. I don't know how long I will stay until I will not feel sleepy. I just want to grind too. Sorry, frustration. So first step, create visited array. So we already got number of nodes, you can say so. So I will mark visited is equals to 0, everything marking like not visited, in range v. Okay, so everything is marked visited, unvisited. Second, create a stack. So I will call it stack, but it is a list simply. Now let's first define a function. Define DFS, self default parameter, that is basically object, holding object. Self is representing, like suppose you are calling. Okay, another thing, so node that you are calling, so node will be there, and from node you will call visited, and definitely you need adjacency, so I will keep it adjacent to it. Add is a. Also don't forget, you need to pass this tag, because every time whenever you are popping, you are appending it. So this is one thing. Now what exactly you do for neighbor, I use same variables, it's easy. In basically add is a adjacency of node. So far you are basically looking for all the nodes that are neighbor of it, I mean that are from this node to the, what is it, edges basically, maybe A, B, C and all. So that's you are looking into adjacency list, and then we got neighbor, and for this we will call if, just check whether it's visited. If not visited, simply you will say neighbor. If it is not visited, then what you will say, self dot dfs of neighbor and adjacency visited. One thing I forgot, stack, don't forget, mark visited of neighbor equals to 1. Okay, so this is one thing, and after that we are calling dfs, and at the end, wow, whenever you are basically this dfs is completed, so what needs to be done? Simply stack dot append. Append means push, so here only you can say append neighbor, you will have appending it. Okay, and okay, this is one thing that is done, visited, if not visited, and at the end, anything I'm missing something or what? So you are calling neighbor, neighbor, neighbor. Yeah, that is all. It looks very simple, dimple. Create stack, and now we'll call for uh, node in basically range v. So for each 0 to v minus 1, if not visited, and what, neighbor, sorry, node, if this node is not visited, then what will do? First mark it visited, node equals to 1. Second, call dot self dot dfs, you are calling dfs. Okay, dfs on node and adjacency visited stack, and finally same, it is whatever we are doing here, we are doing here as well, and at the end stack dot append yeah, just thinking. Correct. It's a stack. So this is the last, means all the dependency or all the nodes that are going to come after it has been already covered and pushed them into stack. Now this is the last one in this node. Yeah, it's into at the starting I thought it's not, I'm not getting what exactly we are doing, but I got the intuition. I don't know about if anyone look into it. So now self stack dot append. Bro, I don't want to show. Okay, next step, stack dot append. I don't, I have to append this node, and at the end I need to return, right? So I need to return or what? Let's see. I need to return, bro. What? Return. Oh, okay. Stack. I'll just reverse. What is the function? I forgot it. Short. Reverse. Is there any function in reverse? Terminal. Python 3. A equals to 1, 2, 3. Let's 4. There is a function. I don't know why I forget these things. Stack dot reverse, but it's not going to return. You have to first do it, then return. I think there will be another thing. Reverse A. Oh, okay. It will be reversed. Sit, it's going to return iterator. I need to call it one by one. So if I'll call, let's say x, just brushing, next of x, next of x 2. Yeah, got it. So return stack. Done. Jai Mata Di. Done. And now let's go to the how to pronounce it first question. I will search it on. I can say hear it in this video only. Tra- Oh, sorry. Is anyone watching? Just curious. It on. I can say one question which I am confused myself. Why did you choose Python instead of C++? Bro, I have to start DSA and I can't decide which language do I choose. I'll tell you. If you are, so simply I will tell you why I choose. I was like when I was in college, I used to do it in C++ only. But recently I observed like I don't need C++ anywhere, and I have to revise every time whenever I'm starting DSA. So I'll type it here only. Sorry, I haven't checked your message. If you are in college or if you are in college or are using already know C++ or Java, then you don't need to use Python because these uh, C++ or Java for far better uh, than Python. Yeah, so far better than Python. Speed and intuition. Like here, there you'll get like okay, you are creating variable. What is the malloc and all. I think I intuition. What the fuck? Okay, intuition will be I am using uh, was using C++ earlier, but observed that I'm just using it for DSA, and most of the time I'm using Python only so thought to switch to it. Sorry, I haven't checked Python only. Huh. I can see the messages here only. And why do you need? Okay, let's do one thing. So now we solved this one topological sort, and now let's go to this second method, BFS, breadth first search. Oh, it's a BFS, breadth first search. Okay, let me try from my end if I can come up with an approach. Just wanted to try out before I jump into another solution. Everything is revolving around breadth first search and depth first search only. Okay, so let's copy this. So this is a graph, okay. And now I just want to use goal. Depth first search we already use. Sorry, DFS done. But what if we want use BFS instead? Still we want to sort. Our goal is to sort it. Breadth first search means what exactly we are doing? I'm tired. It's better if I'll sit on chair. But I don't want to sit all time on chair. So by the way, so suppose I'm starting from 5. So in the DFS, what do you do? So basically, you will start from here and in one direction. Basically, you explore all the nodes. For example, you try to go to this branch first, and then you will go to this branch, correct? And then you will go to this, and in such a way. And at the end, what exactly you are doing? So there isn't any dependency between these two. There is a dependency between this one. But in breadth first search, story will be different. First you will see 5. So you will use Q. So you will store 5. And then you will see, okay, what are the nodes that are at the same level. Then you will store 2 and 0. And for then for 2 and 0. And once you will visit 2, then you will store its neighbors. 3 is there, so you will store 3. Okay, by the way, yeah, so now just imagine after 3 you are going to get into 1. Okay, so first you will pop 2 5, then you will pop 2, and then when you are popping 2, then you will add 3. So this one puttam, sorry. Oh, set what do you what color you choose? This one done, and 2 when you are visiting 2, or when you are basically uh, what we say, when you are popping out something from Q. Basically, you are taking out from a queue one item 5. Then what are the neighbors of 5? You added 2 and 0, and after that you added 3. So if you see both of them are at the same level, then 3 will be at different level. Okay, 3 will be at different level. But you know one thing you will do? After 3 you will add 1. But how to know it? Okay, this is new level. So you can say this is level 0, L0, this is L1, this is L1, this is L2, this is L3. Hmm. So now if you want to do, what you want to do? Basically, if you have to sort it, simply what you will do, first take out L0. After that what you will do, why do I feel like it's already sorted? For example, if I will do something like this, imagine 5 will be there. After that you will say 2 and 0. Okay, then you will get 3, and after 3 you will get 1, and this is one of the queue, one of for one node. Similarly, you will do for it for 4, and for 4 it will be something like this only. In the queue, when you said, you say queue to queue created, both are queue same, but every time you are adding new item and you are starting from there. I think I will do something wrong here. What? Hmm. If I have to do this, in this way, so there it will be something like, first you will add 3 into the queue, then you will add 2 stack. If it is this one, 3 2, then you will get to go to 0, then 5, and after that you can add, sorry, let's say you haven't added, no, you can add 1 as well, then you will add 4. But here 4 should be, let's say there was one more node, 4 should be before it. Hmm. This is one thing. And imagine I started with 4, so it will be like 4 will come first, then will be 1, and then 5 0 2, 5 0 2, and then 3. So all of them are in topological sort, right? 5 4 4 after 1, this is okay, and 1 after 0. This is also before. Right. Okay, it looks like so simply. But let me just tell you my intuition, what I thought if I have to solve it using BFS, breadth first search. So from each node, each no- step one, create a visited array. Okay. Step two, create a queue. Step three, iterate through all non visited nodes. So we are going to iterate through all non-visited node. And step 4, what we are going to do, call the uh, BFS on on a node. You can use this, and whatever result you are getting, like every time, you just need to append like uh, so. For example, you called something and you got result like this result, and now you are calling into another one. So second result, this is result 1, result 2. So when you are combining them, then it will be something like result 2 and then result 1 in the array. Final result will be something like this. Because you solved this, and there might be logically these are two independent parts that you are in the graph that are not interconnected from each other. uh, I mean, you cannot visit from these nodes to this node part and from this part to this part. But it could be this after it. There are some dependencies of result 2 on result 1, as you can see it here. Uh, for example, here we first what we did, simply we called this one. This part we first solved. So this one covered. Now when you call 4, what happens? There is a dependency between 1 and 0. So 1 and 0 should come after 4, right? And that's why whatever you solved first will be last. Whatever you are solving later will be the first result. So why don't I try to, let's try it. Then we'll watch solution. Okay. I mean, then we'll watch tutorial definitely because it's algorithm. So I will watch the video for sure. Hmm. Hey, why don't I drink water? But let me solve first, then I'll watch drink water. So this would be second approach. Will create wasted as usual, not visited. Visited will be 0. Everything marking 0 means non-visited. In a range, you can say v. Sorry. Create a visited array. Second thing, I will do one thing for dq. I mean, to create a queue, we need queue here. So I'm just using collection. To be honest, I never used this module. I just got to know how to create queue and just started utilizing it. Import So there is deck, double-ended queue. So I'm using it as a queue. And okay, create a queue. QUEUE. So DQ is nothing but D deck. And third, iterate through 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 each item, each node. Non, it will help me second time, non-visited node. So for node, no, for node in range, basically 0 to V. These are the 0 to V minus 1. These are the different nodes, and you can say labels of node. So if not, if node is not visited, that means you haven't called it before. Not sorry. If not visited node, then simply call. Okay, what I'll do, result will be simply self dot bfs. I'm calling on bfs on. Okay, let's call bfs on this. By the way, I can use simply loop. I don't need even. Yeah, let's do it. It will be more intuitive. I never used another function for it, but it's better. Let's do node visited adjacency. I think it's better if I'll keep like this node, then adjacency. It's relating to it, then visited, and I'm expecting a result from it. So let's result. And what I'll do, I will create a global result. So this is final result. Result. It will be empty, and every time what you are doing, basically temp temp result is nothing but okay, let's do one thing. Result dot extend what? Result dot extend result. We are just extending whatever the results we have so far. We are just extending it. So this is our new result. And what I'll do, how to do it? Basically, you are copying result, and then this will be, is it right approach? Let's not thought about the data structure right now. It's not important. If not visited, okay. Basically, you calling, and finally you will get result. So return result. Okay. Now time to create a function. Define bfs. I need to pass q as well. Deck. So self node adjacency visited and dq. So I don't want to use. Oh, let's use. It's a new way. So breadth-first search, and while what are you doing? Basically, dq dot push what append. We have append. Either directly append or append. Yeah, append only. Dq dot append. You are appending node, and what you will do here while basically while dq. So while we have items in the dq, so node will be dq dot pop left. Result is nothing but this. So you are popping out item, and then result dot append. Basically you are appending node, and second is option is like what you'll do for neighbor in. Basically you can say adj of node, basically all the neighbors of it, and dq if not visited, then I think I missed something. Visited of node equals to 1, then you are popping pushing it into it, and if not visited what neighbor, then you will post it into queue. Dq dot append neighbor, and also mark it visited. Visited of neighbor equals to 1. So this is the thing that you are doing every time, and you are popping out one by one item, and you are getting result, and at the end you are returning result, and this result is being used there. I think. Why it is printing as well. Maybe it's logging out, logging just the bell. Oh, sorry. This is basically what is my output of it. Did I miss anything? That means my approach is incorrect. Twenty, 27, 25, 20, 15. Hmm. Now I can't debug it. It's a long question. There are so many nodes and see adjacency list. It's a big one. Or what else? Let's watch tutorial. Maybe my thought process is incorrect.
So in this video, we're going to learn about topological sorting, and we are going to use the DFS algorithm. We have done the DFS algorithm in the previous video,
Let me
and
take 2 minutes break to continuously on this. Oh, 13 set. Is anyone watching? I'm only one watching my own video. No problem. Let me just take 2 minutes break, then I will start again. Where is my stream? Break. Chilling, bro. So I'm just back and let's begin again. Here. Um, See how people are studying. Road to emo PD. What exactly you have written? No. By the way, let's do one thing. We have enough. We don't want. I don't want to waste time here. Instead, focus.
This algorithm is famously known as the Khan's algorithm.
On.
Whatever you can call it. So, what is topological sorting?
Oh,
So, whatever you can call it. So, what is the Khan's algorithm?
Khan's algorithm.
Whatever you can call it. So, what is topological sorting? So, it's basically a linear ordering of vertices such that if there is an edge between U and V, U always appears before V in that ordering. So, let me give you an example. So, if I write 5, 4, then I can write something like 0, 2, 3, 1. Okay. Now, this is a valid linear ordering of the graph. What I can do is I can write down all the edges. So let's write down all the edges. So the first edge is 5 0, then 4 0, then 5 2, then 4 1, then 2 3, and then 3 1. So these are all the 6 edges of that given graph. Okay, so we have 6 edges. Let's check out 5 0. So if you see 5 0, 5 appears before 0. So this is 4. 4 0, 4 appears before 0, and that is what the line state. 5 2, 5 appears before 2. 4 1, 4 appears before 1. 2 3, 2 up, and I can have something like 4 5 2 3 1 0. This is also a valid linear ordering. Let's check it out. 5 0, 5 appears before 0. 4 0, 4 appears before 0. 5 2, 5 appears before 2. 4 1, 4 appears before 1. 2 3, 2 appears before 3. 3 1, 3 appears before 1. So there can be multiple such linear ordering of vertices. As long as all the edges satisfy this particular condition, I can say any of that linear ordering to be a topological sort. Now our task is to print any such topological sort. So remember one thing, topological sort or tuple sort is only valid in DAGs. It is only valid in DAGs. What is DAG? It is nothing but directed acyclic, which means does not have a cycle. Directed acyclic graph. Why a directed? Assume I'm saying you have to take an undirected vertex.
Set. What I clicked. Steady view.
Directed vertex, something like 1 to 2. This is an undirected edge between a node 1 and between a node 2. So if you carefully see, this is from 1 to 2 and from 2 to 1. So in the linear ordering, you can't have such a linear ordering such that 1 appears before 2, at the same time 2 appears before 1 because the edge is bidirectional. If we call it an undirected graph, thereby it has to be a directed graph. What about acyclic? Let's understand. So imagine I draw 1, then I go to 2, then I go to 3, and then I go to 1 back again. So there's an edge between 1 to 2, there's an edge between 2 to 3, there's an edge between 3 to 1. So what I'm saying is, in the linear ordering, 1 should be before 2. So 1 to 3 is
Same.
where logic data structure. This is nothing but the first and first term data. Over here, we know what we need. We need a data sorting using the DFS. And since we are using DFS over here, we know what we need. We need a data structure. This is nothing but the first and first term data structure. This is the particular adjacency list. And this is a new thing that we will introduce because it is not exactly the BFS algorithm, slightly modified version of it. So we're going to use an degree. What is the definition of an degree? Number of incoming edges to a node. Yes, very important. Number of incoming edges to a node. I have already taught you about this in the first video. So if I ask you for 0, what is the number of incoming edges? Can I say it is 2? So I will say the number of incoming edges for 0 is 2. For 1, how much is it? It is again 2 because there are 2 incoming edges to 1 as well. So 2. Now if I ask you what is for 3, there's just 1 incoming edge. This is outgoing. So in degree is just 1. So this is, sorry, for 2 it is actually 1 because there is 1. For 3 also there is 1. And now for 4, are there any incoming edges? Do you see any incoming edges?
0.
No. So you'll be like 0. And for 5, are there any incoming edges? No. So you'll be like 0. Now what was the definition of tuple sort? If there is an edge between U and V, U appears before V in the linear ordering. That was the definition of tuple sort, right? So can I say, since 5 and 4 do not have any of the incoming edges, so you can place 5 or 4 at the starting. You can place either 5 or 4 at the starting of your linear ordering because there has to be no one before 5 because there's in degree is 0. There is no one before 5 or 4. You can place them at the starting. So what you do is you say, okay, initially there will always be a node. There will a minimum of one node whose in degree is 0. So step 1 is very clear. Insert all nodes with in degree 0. With in degree 0. So can I say I'll insert 4 and 5? You can do 5 and 4 as well. So I've inserted 4 and 5. Okay. Now the ordering can have 4 and 5. Now 4 and 5 would be having the incoming edge to someone, right? So they were getting into someone. So what edge to someone, right? 5 would be having the incoming edge to someone, right? So they were getting into someone. So what I'll do is I'll take 4 out of this. I took 4 out. The 4 was into someone. Let's see. 4 was into 0 and 4 was into 1. So I mean, like, let's take it off because I already have 4 before it. So I'm placed in my ordering 4. So I have 4 before it. So from 0, take out 4. So the integrate will reduce to 1. And from 1 also take out 4. So the integrate will reduce to 1. So what I did was I said, let's take it out. is let's take it out. So kind of you can say I remove these edges. I kind of remove these edges. I'm saying take them out because they're no more into consideration. Okay, perfect. So I've taken them out, right? After taking 4 out, is the 0 having an integer 0? Look, there's still a lot of edges which are into it and are not yet in my direction or in my linear ordering. Okay, fine. So I've done the work for 4. Next, take out 5. So 5 will be in my linear ordering. Like 5 if you see is entering 2 and is entering 0. So if I take it out from 0, the integer will become 0. So the integer of 0 now becomes 0. So you can take that 0 and put it into the queue. And from 2 also you'll take it out. So the integer of 2 will also become 0. So you can put that out as well. Perfect. Now, can I say, since you took 4 and 5 out, 4 and 5 was already entering 0. Thereby the integer becomes 0. So you're very sure that you have placed 4 and 5 before. Right? Now, when you take the next element out of the queue, it is 0. And you can place that into the linear ordering. Because it is now an integer of 0 because 4 and 5 have been taken out. Got it? Perfect. For 0, you will see, does it have any anywhere, any adjacent nodes? No. So nothing to be done. Next you take out 2. Where is 2? Adding 2. 2 is adding to 3. The adjacent node of 2 is 3. This picked up out as well. 2 0. The integer will become 2. Taking 4 out. Is the 0 having an integer 0? Look, there's still a lot of edges which are into it and are not yet in my direction or in my linear ordering. Okay, fine. So I've done the work for 4. Next, take out 5. So 5 will be in my linear ordering. Like 5 if you see is entering 2 and is entering 0. So if I take it out from 0, the integer will become 0. So the integer of 0 now becomes 0. So you can take that 0 and put it into the queue. And from 2 also you'll take it out. So the integer of 2 will also become 0. So you can put that out as well. Perfect. Now, can I say, since you took 4 and 5 out, 4 and 5 was already entering 0. Thereby the integer becomes 0. So you're very sure that you have placed 4 and 5 before. Right? Now, when you take the next element out of the queue, it is 0. And you can place that into the linear ordering. Because it is now an integer of 0 because 4 and 5 have been taken out. Got it? Perfect. For 0, you will see, does it have any anywhere, any adjacent nodes? No. So nothing to be done. Next you take out 2. Where is 2? Adding 2. 2 is adding to 3. The adjacent node of 2 is 3. So you reduce the integer of 3 by 1 and become 0. So now you can take 3 and put it into the queue. Perfect. Next, you take out 3. Now you have 3. 3 is saying, who am I? You can take out 3 and 3 was getting into 1. So 1 will now reduce its integer to 0. So now you can take out 1. Perfect. You can remove it. Currently this integer will become 0 and this will be done. So apparently I have 1. So you can take out 1. And over here you can place out 1. So does 1 have any adjacent node? No. So I can say at the end of the day, we have 4, 5, 0, 2, 3, 1 as a valid 2-pole sort. So what I did was super simple. I insert all the nodes with integer 0, take them out of the queue, and just remove the adjacent, just reduce the integer of the adjacent nodes. And if the adjacent nodes have the integer 0, I say them, you have you guys set before, so you can now go to the queue because you will be a part of the group sort. Got it? So quite simple. Quick question: how do you figure out the integer? How do you figure out the integer? Very simple. If I'm saying 2 is having an adjacent node to 3, which means 2 is directed to 3. So can I say the integer of 3 will increase by +1? So what I do is I traverse in the adjacent node, and whatever is there, I say integer of 3 can do a ++. If there is 0, I can say integer of 0 will do a ++. If there is 1, I can say integer of 1 will do a ++. Because if I'm saying 3 to 1, it means there's an inner edge to 1, there's an incoming edge to 1. So very simple, you traverse in the adjacent node and you can increase the integer. So we will now go back to the code editor. As usual, the speed. So very simple.
Got it. It's a cool one. It's algorithm like, so it won't work. Let's do one thing. First step. Step 1, build the int degree array. So int degree is equals to this, and what you'll do for each v in, or you can say node, it's better if I use v, vertices in range of v. So here, one thing, don't forget 0 for underscore in range v at a starting URL, so that you can create a blank array for each v. You will get for let's say u, and it will be v. in ADJ of u. So basically u to v there is an is. So for v it will be in degree. So in degree of v plus equals to 1. Basically you are adding, and now you got in degree. First you will say result, so blank, and create a DQ. I mean from collection, import DQUE deck. DQ equals to DQUE deck. We create a deck. Now for basically v in degree in range v, if in degree of v equals to 0, then what you will do in degree, basically dq dot append, and here you will append v. In degree 0 you are starting, and now what you will do while dq, so while there are elements in the queue, so basically what you will do, these are basically in degree 0, you are maintaining all the basically in the queue you are keeping only the in degree 0 items, 0 vertices, not item. So you pop out one, basically v equals to dq dot pop left. Okay, so you got vertex or node. Now you will say result dot append, this is in degree 0, append v, first thing. And now what I'll do, all the edges that are going from here, you will mark them basically. So you will check. For neighbor in ADJ of V. So you are looking for all the neighbors of adjacency. Basically, this particular is particular vertex. All the neighbors will be there, and you are looking for the neighbor. Basically, all the neighbors you will check. Minus equals to 1, so you are reducing basically. And what I will do, if in degree of neighbor equals to 0, then dq dot append neighbor, and you are going to do this all times, and at the end return result. So let me just think more about it, what exactly is happening here. First we created in degree, everything is in degree, and whatever the nodes that are in degree 0, that means there aren't any dependency. So if there isn't any dependency, you can basically push them, and you can keep in any order, correct? Now what exactly you are doing, every time you are basically you are looking for all the nodes that are basically all the out degree of a node. are basically all the nodes that are going from U to V. So what exactly here is happening? You pulled out one node within degree 0 that is part of this DQ. You appended it into result. Now you are looking for all the neighbors, and I'm just thinking about it. Will it be condition where I need to keep visited? I don't think. Yeah. So neighbor in adjacency V. So whatever the neighbors of it are, basically all the not the right neighbors. Yeah, neighbors only. So you are picking up and you are reducing their in degree, because now you are reducing the number of edges. Basically, you are covering whatever you covered and removing them. Will I remember it? This algorithm. Definitely, I think I need a revive to review. Why are we removing it? How it is going to help us? When you are doing something, first let me just correct. So result is okay. I just want to draw it first to get the intuition. Else I will forget in 2 days only. Where is my? Yeah, you are here. Let's say we have node from 0 to 1 and 1 to 2 and 1 to 3. So 0, it will be 0, and let's say there is one more 5, 4, and let's say 5 in such a way. So 0, so for 0, 0, 1, 2, 3, 4, 5. Okay, everything is 0 at starting. Let's keep for 0 in degree 0, for 4 in degree 0, and for 1, so basically 2, for 2 it's 1, for 3 it's 2, for 5 it's 1. So what are we going to do? Basically we'll be having one queue. So at starting you have 0, there are two nodes 0 and 4. So you will push 0, you will push 4 into the queue. Okay, now exactly what is happening. So you are just taking out 0 degree and 0 degree, and now you will start popping out one by one, and you will take out 0, and now what you'll do, all the nodes that are going out from the 0, so there is only 1, so you will check for 1 what is in degree. So basically you are breaking this linkage. Now you will say okay it's 1, then you what you'll do, simply you will reduce it to 0, and when you are reducing, then you will check whether in degree of this is after modification it is 0. If it is 0, that means oh, just come into queue. Now you will try, so it will say 2, 2 will be part of it. Now will again pop out one more thing 4, and for 4 you will check okay there is 5, there is 1 and there is 5. So you will say okay, for 1 let me check what is the degree. So it will change it to 1, and For 5, you will say okay, it will change to 0. So you say okay, 5 having 0, then let's put 5 into it. So you kept 5 into Q, and now okay, so this is 10. Now you'll cut 2. Basically you will uh, pop one more item, that is 2, because it's turn first in first out. So 2. For 2, you will check again what are the adjacent or out edges from it. So it's at 3, it can reach to 3. For 3, you will say okay, no problem, 3. For 3 there are 2 edges, so let's mark them reduce by 1. So 1. So now you won't do anything. So for 2 you won't do anything. Now you will pull out 5. So you will say 5. You will say 5, okay. 5, no edges. What the heck? What happened to this? 1 and 3. Something wrong. Why didn't it come 1 and 3? First you kept 0 and 4. When you were processing 4, what you did? Simply reduce 5 to 0 and 1 to 0 will be there, right? So you kept 1. So 1 will be 0 for processing. When you are processing 0, when you are processing 4, it will be 1 here somewhere. So 1. Something I messed up. Let's do it again. By the way, I got it. But let's do. This is our Q. At starting, what will be having? For 0, it will be 0. For 4, it will be 0. For 1, it will be 2 in degree. For 5, it will be 1. For 3, it will be 2. For 2, it will be 1. So this is one condition. So we'll push 0 and 4. You can push in any order. And after that, what you'll do? You'll take out 0. You will add it into result. So you just, I'm keeping here result 0. And what are the neighbors of 0? 1. So you will say okay, 1. Just remove its degree and reduce it to 1. I mean just reduce by 1. Now you will say okay, zeros rolled in. So now it's 1. 4, you will take out 4 and you will say okay, remove the degree of 5 by minus 1. So it will turn to 0. So you will add 5. Now you will say 4, 1. So remove the degree of 1 by 1. So you will remove it to 0. So here you will add 1. Now what you will do? So you will jump to 5. So okay, so what exactly we did? So 0, 4 we got result 5, and for 5 you will say nothing is there, 5. So 5 will come into it directly, and then 1. What are the basically edges from it? So you will say 2 and 3. So for 2 you will mark 0, and for 3 you will reduce by 1, and from 2 you will add it into it. Now you will just go to 1, and 1 you will say what is degree but basically 1 you will from 1 you can go to 3. So 3 you will turn it 0, 3. So 1, 2, 3. This is one option. Let's do one then. I already did it. So fuck. Am I watching my video or what? So fuck. Madam, where am I watching my video? Video. Let's do anything. Just the camera is not visible or what? Oh, it's working, bro. That's not good. Let's do. What is the duration of this stream so far? Just 2 hour IMS today. No, it's not. 4:44. Let's do it, bro. I don't care. Time is just okay. So I am saying LinkedIn. I'm hungry, but I don't know. I don't have anything to eat. I have it in the night. Just there are some fruits. Okay. So this one is done. But you I already solved it. So why would I solve it again? Submissions, BFS. See, it's the same problem. Topological sort, cons algorithm, cons algorithm. Okay, let's do one thing. I don't know. I already solved this problem, but just wanted to see how we are going to approach it using Hans algorithm. So let's say we have 0, then we have an graph, like we have a graph like this 2, then we have 4, and from here we are going to 3, and here we are going to sorry like this. Now if you notice, let's say here we have one more thing 5. So these are the nodes, and there is a cycle, and topological sort work for DAZ acyclic. but how can we detect it? Just I'm thinking, maybe will what comes into my mind. I feel it might be like there will be some nodes where in degree will still be remaining, and because of that you can get it. Maybe let's say 0, 1, 2, 3, 4, 5, and for each 0 there is 0. For 1, for 5 it's 0. For 1 it's 2. For 2 it's 1. For 4 it's 1. For 4 it's 1. For 3 it's 1. For 2 it's 2, sorry. For 3 it's 1. Okay, so these are the nodes. Now what needs to be done? Okay, let's start. Let me use a different color to draw Q. So this is our Q. Push the in degree 0. This one and this one will be pushed into Q. So 0, 0 will be part of it, and 5 will be part of it. These are the nodes name. Label, these are the in degree. I will let's mark it as a in degree, in degrees. Okay, 0, 5 will be there. Perfect. Now 1, 2, 2 and 1. Hmm. So now you will take out 0. So in the result, or you can say 0 will be there. And let's say I'm not storing anything result. Just I took take out, or took take I have taken out 0 out of it. Now only remain 0. What are the nodes for 0 to 1? There is a in degree outgoing is, so 1. For 1 you will reduce the number, so it will be, now it will change to 1. And for now what you'll do, you will go to 5. And okay, for 5 you will say okay, 5 having a degree going to 1, 5 is having an is going to 1. So for 1 you will mark 0. So 5 will be out and 1 will be part of it. Now from 1 to 2 you will go, so 2. So what you will do, basically you will take out 1 and you will do, okay, what you will do, so take out 2, no, take out 1. So 1 you will remove degree and it will be 1. 1, correct. And after that you don't have anything, Q is empty, but still there are some errors. But I just wanted to know the logic behind it. Why? Suppose if I have changed it to something like this, suppose there isn't any S. Oh, then 3 will be part of this and 0 will be the unknown. So I think this is very simple approach if I have to solve it. Let me do it. I'm so sorry. Where's my boss? No one is was saying. Solve it using cons cons algo. I have BFS. So I'll do anything from collections import deck dq, and now dq is equals to deck, and now in degree. In degrees, so in degrees will be something like 0 for underscore in range, v for each it is 0 placeholder. Now for each vertices in range v, what exactly we are doing, we will iterate through, uh, that's why I take u and v in adjacency of u. So all the vertices in degree for this. So you will say basically in degrees of v is equals to plus equals to 1. Now apply BFS for in degrees for v in range v, if in degrees of v equals to 0, so dq dot append v, and while dq there are item, node will be dq dot pop left. Basically you are taking out one item, and what exactly you are doing, you are going to look for the neighbors of it, for neighbor of in adjacency of node. So basically this is these are the neighbors of adjacency for this particular node. And now you'll say in degree of neighbor minus equals to 1, and if in degrees of neighbor equals to 0, then dq dot append, you will say neighbor, you will append it, and finally until this process is going on, and at the end for v in range v, if in degrees of v not equals to 0, because if you finish the queue and still there are some items where in degrees are coming, return true. Oh, where are it len of result? Did I solve it in wrong question? What the heck, bro? Where are you doing? This is not the problem that I wanted to. Submission, editorial, not this. will change into V. Adjacency will remain same. Hmm. From collection, my what do you say? Knees started aching because most of the time I'm sitting on chair only. I don't know because I have to fold my uh, knees. This is very bad. From collections, import deck. Bro, this is interesting. I solved it using something where I was using stack and all, but it is very simple to solve using algorithm. Solve Game of Throne. Okay, so this is one of the BFS approach where you are just checking whether if still there are in degrees or not. And another option is depth first search. What exactly we are doing in depth first search? We are sorting. So how to use DFS here? What I'll do simply pending depth first search uh, using topo. So I'll keep it. I'll park it because I'm continuously solving one problem only. But I'll keep it unchecked. Course schedule fun. Let's take 1 minute break. I just want to scroll reels for a few minutes. Because my crazy legs. I don't know if even if you can see me. Oh god. I'm sitting on the clock. What the heck? Cam oven. Just keep it aside so I don't look ugly. Now I will do anything. So I have to keep it here. Hello. Just let me take 5 minutes break. Break. Oh, anyone was? I have to keep it here. Hello. I don't know. I just want 2 minutes break. I just want to scroll reels, bro. Maybe 2, 3 reels. Because I'm continuously. But I'll change. You will just hear audio might be. So next problem I'll solve. Just I'll take 5 minutes break. See. Bhai, let's. Oh, sorry. Where is my transition? What the heck? Transition live stream. Okay. Yeah, let's start. Pack. Today I just listened to a song, and this is not needed. This is not needed. I will minimize it. Let's do it. Let me stop it. And what I'll do? Speed test. Stop it. Topological sort. I got it. This one. What is topo sort? This is done. What is this? This is not needed. So this one is also done. Let's jump into another problem. So I parked it for the timing because one approach I solved it using the topo short. I mean DFS and depth first search. I need to work on it. Like how to use detect cycle. We already solved it using a. I solved it using my own approach, but here I need to use this uh, algorithm topo short course schedule. Let's see this is what kind of problem it is. There are total of n tasks labeled from 0 to n minus 1. There are a total of n tasks labeled from 0 to n minus 1. Okay, given an array where array of I equals to a and b indicates that you must take course B first if you want to take course A. There are total n tasks labeled from 0 to n minus 1. Given an array indicates that you. But what is the meaning of I here? A and B, these are the tasks. Okay, so there isn't any relation between this and this one. So you can say these are the different ages. For example, here you have to take 0, then only you can take 1. Here you can take 1, then only you can take 2, 2, then only you can take 3. So it's also kind of what I'm thinking. It's sorry, I'm just. I mean, yeah, it is also cycle detection problem only. If you are able to solve, then it is. So basically, if you can if you can sort them topologically, then that means you can finish them. But if you are unable to solve them, there will be two approaches. And let me just draw it. Sorry, I will sit here only. So we have 1 0, 1 to 0, 2 to 1, and another one is 3 comma 2, n equals to 4. Okay, so how it will help us? Like n equals to 4. It will help us like, okay, suppose here maybe let's say only 1 0 and 2 1 is given. Then you can say all other tasks are independent one, you can take them. So what I'll do, I'll build a graph. 0 to 1, this one. So there is dependency. First finish this. So A to B means first take out B, then only you can take A. So priority will be 1, priority will be 2. So 0 to 1 there is a ace, there is an ace, and 1 to 2 there is an ace, and 2 to 3. So it says linear graph, 2 to 3 there is an ace. So yeah, it is possible. Okay, let's do one thing. False one. So 0, let's do one thing. I will draw directly. Second example, array is given like 0, 1 and 3, 2, another one 1, 3, 3, 0. This is another example, example 2. So what you will do, there is an ace between 1 and 0. You can see this one. Then 2 and 3. Then 1 and 3. Sorry, 3 to 1. And here you will see, wait a minute, yeah, 0 to 3. Now there is a dependency that you cannot fulfill. This is a cycle here you can see. So as usual I will use same approach. Topological sorting. Simple, it's simple dimple. So let me keep it aside and let's solve it. It's like I'm just revising topological multiple times. I will use BFS because it feels more intuitive, and I'm not sure if cycle detection because I haven't used DFS yet. So breadth first search. What I'll do, simply first I will make a adjacency list. So for 0, for underscore in range n. So these are nothing but you can think these n tasks are nothing but n different vertices, and all the labels it could be like, suppose here we have 4, but it could be like 1, 0, 2, 1, 3 and 2. There is an 3 inclusion of 3. Then you have to, it will be like an independent node. So for v in range n, so what will do, ADJ of v, added some blender, I'm sure. This is this one. What for array? So for edge in array. So what you'll say, u comma v is nothing but, I will use u v comma u because u is equals to s. Okay. Now you will mark adj of u is equals to dot append v. So u to v there is a ns in degrees. For okay, for I mean I'll keep it in my laptop in lab. That's why they kept the name laptop on top. Otherwise they should keep that's why there is desktop laptop. So we should keep it in lab. Not always. By the way, okay, I need to calculate, basically count the in degrees. So for first I will do one thing. In degrees is equals to 0 for underscore in range not raise n placeholder for basically v in a range n. So for each vertices you are going to check what are the edges for it. So for uh, node in adj of v, what are the nodes, and then what you will do in degrees of node plus equals to 1, because these are from from this v to node there are edges, so you got in degrees. Now next thing, up create a queue from collections import dqut. So deck dq is equals to deck, and here we got deck. Now dq dot just append for v in range n if in degrees of v equals to 0. Simply what do you do, dq dot append basically in degrees, no v will be appended because it is having 0. Now what you'll do, while dq, every time whatever you are going to do, simply you will take out one item from the dq, and that is having 0 in degree. So node will be dq dot pop left. Now if not this. So now what I'll do for this node, and now we'll check all the neighbors in adj of node. So basically you are going to check all the neighbors in adjacency of node, and what you'll do basically in degrees of neighbor minus equals to 1, and if in degrees of neighbor equals to 0, what does it mean? Okay, if in degrees of neighbor is 0, if in degrees of neighbor is 0, sorry, I was thinking something else. Neighbor equals to 0, what does it mean? It means dq up blue just append what neighbor there, and at the end check if there is a cycle, then take and go for a drive. Neighbor, then what will do, v in range n if in degrees of v not equals to 0, return false, return true. Coding for you. Then bro, done. It is. I think this one will be interesting one. Imagine I'm doing every day 10-20 problems. It's very hard. Sometimes it's easy, but when it comes to array and all, mind goes blank. This one is medium. They kept this one hard, this one medium. Let's see. Then why they kept it in part two? There are total of n tasks labeled from 0 to n. A given array indicates that you must take course B first if you want to take course A. Find the order of tasks you should pick to finish all tasks. If no such ordering exists, return an empty array. Any answer you can return. Perfect. So what's new in this? It's just instead of printing like whether it's possible or not, you are just going to okay, let's do it. I mean, just it's simple. You have to return if it is possible. If there isn't any cycle, then you can return the topologically sorted result, and if it is not possible, just return false. I mean, empty instead of false. True or false. Just so again, we are going to use BFS only. So I feel like I'm just repeating the same things again and again. Why don't I learn the DFS as well? I mean, yeah, topological sort can be done by both approaches, but how will I detect cycle? That is one thing, right? I know how to sort it. Let's park it. Let's do it using BFS only. At least I will learn one approach. BFS. Okay. First thing, we have array build adjacency. So adjacency is nothing but for underscore. Yeah, it's like a revision and in a range n. So this is our adjacency for 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 a reason. I mean, yeah, for is in array. So you can say b and u is nothing but age you got, and what will do adjacency of u should be okay. Adjacency of u dot append v. U to v there is an age. First you complete u, then complete v. Okay, this is done. Build in degrees. Degrees? I don't know. Okay, now in degrees is nothing but this one, and no, not this one. 0 for underscore in range, and here you will say n. So this is one in degrees. Now what I am going to do, so we need to construct it. So for v in a range n, what exactly you are going to do for node in adjacency of v, so all the nodes of it, and then so what next step is, so you got node adjacency node, and you will do one thing in degrees of node plus equals to 1. Okay, perfect. Now apply BFS. From collections import DQ deck. Let's create deck DEQUE deck, and then while no first append for v in range, and if in degrees of v equals to 0, then dq got append, and you are going to append v. This is one step. Now just start BFS while dq. What exactly you are doing? Node You are basically popping out DQ, pop, left. You are popping out one item, and what exactly you are doing? Well, I mean, I'm repeating same phrases. Set. So you pop, you popped one item out of queue, and now, so this these all the items that are in the queue are having zero, like basically in degree turned zero for them. Then only you are appending into, basically you are inserting into the queue. Okay, having degree zero. Now you will check, okay, for neighbors in uh, ADC of D node. So you will check the neighbors of it, and what you will do in degrees of neighbor minus equals to 1. Basically you are reducing the in degree, and you will check if in degrees of neighbor return, not return, dq append neighbor. I think I'm missing something. Result I need to store, right? Hmm. Result dot append node. You are appending. So don't blindly return the result. First check for v in range n. If in degrees not equals in degrees of v not equals to 0, simply return blank string at any step. Return result. I don't know why, but I feel like I will forget it. Right now I'm in flow, so I know what to do. Revision must be done. So this one is also done. Simple, dimple. I just solved these problems only. I feel like it's been long time. I'm find eventual safe state. My life is getting hell. Oh bro, someone pinged. Sorry, I'm not looking into chat. Let me respond. Oh bro, someone pinged. Sorry, I'm not looking into chat. Let me respond. What is DSA? Someone is asking. Data structure and algorithm. I think you are not structure and algorithms. What is DSA? Someone is asking. Data structure and algorithm. It is related to programming, I'll say. Structure and algorithms. Sorry. How to tag someone? Okay, no problem. Good morning. Oh, it's 4:34. I'm not leaving you right now. By the way, let me drink water. Water. Oh, let me keep it as it is. So this is me. I'll be back in 2 minutes. Just okay. I'm, I'm back. Oh, why are you learning this? Bro, just let me verbally tell you. Okay, so I think if you are not from the coding background, then you don't know the exact use of it. But in coding, when you are appearing for any interview, and especially they are checking whether you are able to solve the problem. So basically, it's more about problem solving skill. It tests your problem solving skill. They will give you a problem, and you have to solve it. So these are the different kind of problems, and the main reason behind learning it is simply whenever you are developing a software or something, you have to optimize it. Basically, you have to minimize the memory consumption, and you have to use optimized approach to solve it. So that, for example, I'll tell you a simple scenario. Like suppose you are visiting a Flipkart or any shopping cart, like Flipkart or Amazon. For I'm telling you in simpler term. Then suppose it's taking more time. Let's say you are waiting for 1 minute, and then you are seeing the web page. Then you won't like customer retention will be very low. They will switch to another website. Maybe if you are the issue is happening in Amazon, then you will switch to Flipkart or maybe any other shopping website. So the developers role is to optimize the backend code, and for that they are using different algorithms. Not always they are using algorithms only, the other stuff is also going on. But when you are developing softwares or something, you have to optimize them, and for them you are using algorithms, and that's the use of data structure and algorithms. So yeah, I think I'm clear. Let me dock it again. How to dock it again? Bro, I just want to dock. Come on. Holy moly, shit. What happened to my screen? Oh, something wrong. Top chat, what is this? Live chat. Not using this. What happened to OBS? Docs, log docs. Yeah, so I can see it at least. My network is also slow. I don't know. No, it's okay. Chat. Oh, shit. It is taking full width right now. Leave it, bro. Let's jump to another problem, because find eventual safe states. Okay, first let me read the problem carefully. Given a directed graph, okay, so directed graph, that is the thing. So with v vertices labeled from 0 to v minus 1. Given a directed graph with v vertices labeled from 0 to v minus 1, the same story. The graph is represented using an adjacency list where adjacency of I list all nodes adjacent to node I. Okay, same story. Meaning there is an ace from I to each node in adjacency I. Okay, a node is a terminal node if there are no outgoing edges. A node is a terminal if there are no outgoing edges. Okay, so all the nodes are like in degrees only. For example, here I could see 5 is one of the in degree. 5 is a terminal. Is there any other terminal? From here it is going, from here it's going, outgoing. Okay, from here also, from here also, and for this one also it will be like 5 and 6 will be here. A node is a safe node if every possible path starting from that node leads to a terminal node. A node is a safe node. Mhm. Okay, I mean, still, one thing when you are solving topic by topic, you you have to think around particular algorithm only. So this is one of the easiest part. But when you will solve randomly, like when I'm solving lead code, you have to think about different algorithms and you have to scan through all the possible algorithms. Sometimes it's easy to pick, especially if it's relating to a graph or something. You can get it easily. You can get the pattern. For example, here, but still you have to think like it's BFS, DFS, or topological sorting related. I know it's just a language tweak, and you have to count all the nodes. Just last part is tricky part. Really feels to me. Okay, my mic is just given a directed. Okay, this is the clear. This is till here. It's clear. A node is terminal. This is also clear. No outgoing oasis. So we need to find a node is a safe node if every possible path starting from that node leads to terminal node. For 0, 0 to 5. What? 0 to 5 and 0130. 0130. Second path does not end at the terminal node, so it is not a safe node. But bro, why don't you just do this 0130235? This is also path, right? From node 2, only one path. From node 2, only one path. 2 to 5. Yeah, 2 to 5 only. So this is a safe one. From 3 to path 3013. From 3 30, huh? 3013. Okay, it's a cycle. But why don't you do 301013 or 3025? 3025 also it considered one. Okay, okay, it's like this way. From 3 you will start, you will go to 0, and now you have two options: either go one in this way or go in this way, in this direction. If this direction leads to uh, a terminal path, this one leads to a cycle, and you won't reach to. That's why 3013. From 4 only one path 5. 6 is a terminal node, so it is safe node as well. Okay. Hmm. How to solve it? How topological sort will fit into it? We need to count, not count, but we need to find all the safe nodes in ascending order. Hmm. Here, which node is terminal? 3 is a terminal node. From 0 you can go to 1, 2 and 3. But what's wrong with it? From 0 you will go to 1, from 1 you will go to 2, from 2 you have two options: either go to 0 or 3. 2546. It is like the nodes that are part of cycle won't be considered. But how to? Hmm. Let's do one thing. Let's do some rough work. Rough work. Rough work. Hmm. So what I'll do? Simply let me draw this 0, 1, 2, 3, 4, 5, 6. 0, then 1, then 3. Seems like my internet is also fluctuating. Let me check if someone pinged me. Seems like my internet is also. Zero one, 0, 1, 2, and 3, 5, 4, 6. What if I'll do it? This is a prop. This is basically a graph. Now I feel like I should go to bed because I'm hungry. What's the word for it? 0 to 1, 1 to 2. Let's think. I mean, yeah. Otherwise, what's the point of grinding? So you have 0 to 1, and this cycle, all the nodes that are part of cycle are being discarded. Other than those nodes, let's think about it. Node can be a part of a cycle. Else, can we say that node will be part of list? Let's just draw a few couple of graphs. So 0 to, let's say 1, and 1 2 3. So let's say this is one option. Now this, see, 0, this is one of the option where it is not. From 3 you can reach to 1. So okay, from 0 you can reach to 3 1, or you can say 0 to 1. So this is one of the terminal. You can go from here to there. I'm just trying to figure out, okay, I mean, if I'll use in degrees, and will it work? 0 1 2 3 0 1 2 3 4 5. So this is one of the basically in degrees. I'll keep everything. For 0 in degrees 0, for 1, uh, for 0 it's no, for 0 it's 1, for 1 there is in degree 1, for 2 it's 2, for 3 it's 1, for 3 it's 1, and for, sorry, 3 it's 1, for 4 it's 0, for 6, sorry, there is no 6 as well, for 6 it's something like, okay, for 5, what is the in degree? 2, for 6 it's a 0. So what I'll do, let's do one thing. We'll be having q. Okay, at the starting what you'll do, nodes having 0 in degree, you'll push them any order. So I'll push 4, I will push 6. Now what I'll do, 4 and 6, you take out 4, then corresponding to 4 will look what is the age coming from 4 to 5, there is an age. So 5, for 5 you will reduce 1 in degree because you are able to access it 1. And okay, now you will say 5, still it's there is value. 5 it will be 1, and 6, okay, now 6, for 6 you will check, you will just take out 6. Six, you will take out 6, and 4 and 6, bro, it's not going to work. I mean, just 4 and 6 and ended up q is still having the values. 013. Basically, but I know one thing. Basically, a goal, remove nodes that are part of cycle. Not working. Let's take break. I mean, not break. Just I'll stop streaming. I hate. It's morning, early morning. Let me see if anyone thinks. What happened, bro? I'm just stopping because my brain stopped working. But very bad. Maybe I'll study still, but I will start again. It's not over. I mean, I'll take a nap, then I'll start. DSA now I'm going to grind it. No more bakwas. Bye bye. And if anyone is gonna watch, good morning, guys. Happen.